Assistant Professor in the Department of Mathematics, ITR, SOA deemed to be university. It is my great honor and privilege to welcome you all to the International Conference on Computational Mathematics for Engineering Sciences and Healthcare, in short ICCMESH 2026, organized by the Department of Mathematics, Institute of Technical Education and Research. It is my great honor and privilege to welcome you all to the International Conference on Computational Mathematics for Engineering Sciences and Healthcare, in short ICCMESH 2026. Sorry for the disturbance. So your gracious presence has made this occasion truly special, and we sincerely thank each one of you for joining us today. I now kindly request all the respected dignitaries to take their seat on the dais, please. Yes, sir. We can. Sure. We can do that. May I now request everyone to kindly rise as we begin the inaugural ceremony by the lighting of the ceremonial lamp, followed by the SOA anthem.
दीपज्योति परं ज्योति दीपज्योति परं ज्योति दीपज्योति जनार्दनः दीपो हरतु मे पापम् दीपज्योति नमोऽस्तुते शुभं करोतु कल्याणम् आरोग्यं सुखसम्पदः द्वेषबुद्धिविनाशाय आत्मज्योति नमोऽस्तुते आत्मज्योति प्रदीप्ताय ब्रह्मज्योति नमोऽस्तुते ब्रह्मज्योति प्रदीप्ताय गुरुज्योति नमोऽस्तुते.
Can I request everyone to kindly keep standing for the SOA anthem now?
जय भारत वर्षोत्कर्ष विधायिनी जय विश्व विजयिनी जय विद्ये जनगण मनोरञ्जनी जय हे जय जननी शिक्षानुसन्धान रक्षा विद्या प्रदाने सुदर्शा भुवने जयतु प्रयुक्ति परशाला क्षेम प्रवर्तिनी शीलेन लोला विज्ञान नैपुण्यमाला भुवन
May I now request the dignitaries to kindly take this seat on the dais, please? Thank you, everyone. We shall now proceed with the bouquet presentation. So I now invite our organizing team to present the bouquets to our esteemed guests as a token of our warm welcome. Let us welcome them all with a huge round of applause, please. Do not cross over. To commence the inaugural session, it is my privilege to introduce Professor Sunita Chand, Organizing Chair of ICCMESH 2026. Professor Sunita Chand is the head of the Department of Mathematics at ITER, SOA deemed to be university. With over 26 years of dedicated teaching experience, he has been instrumental in nurturing both academic rigor and research culture within the department. Her research expertise spans ordinary and partial differential equations with a special emphasis on fractional and functional differential equations. Ma'am, may I kindly request you to deliver the welcome address?
Thank you, Bilipsa. Good morning, Honorable Vice Chancellor, Shiksha Anusandhan, deemed to be University, Professor Pradipta Kumar Nanda, respected Chief Guest, Professor Sanjeeva Pereira from University of Colombo, Sri Lanka, respected Professor Manjula Das, Ma'am, Controller of Examinations, SOA, DU, respected Dean Sir, ITER, SOA, DU, Professor Pradeep Kumar Sahu, convener of the conference, Professor Mitali Madhusmita Naik, co-conveners, Dr. Pinaki Prasad Kar and Dr. Sobhagya Kumar Sahu, distinguished invited speakers and delegates of the dais, heads of the departments, invitees, participants, members of the electronic and print media, my dear colleagues and students. It's a great honor for us to organize the International Conference on Computational Mathematics for Engineering Sciences and Healthcare, ICCMESH 2026, from 6th to 8th August 2026. I take this opportunity to welcome all the delegates and the participants of this conference from different corners of the world on behalf of the organizers. The conference is organized by the Department of Mathematics, FET, ITER, SOA, DU. Our department has 45 faculty members and 2 supporting staff. The department has been consistently striving to excel in both academics and research since its inception nearly 30 years ago. The faculty members of the department are actively involved in research in various fields. We have been conducting workshops, faculty development programs, and conferences regularly. Today we are embarking on a 3-day journey as we begin the international conference in Computational Mathematics for Engineering Sciences and Healthcare. This conference will be in hybrid mode. The objective of this conference is to provide an interdisciplinary forum for researchers and academicians where computational mathematics meets real-world innovation. The conference will enable us to gain an insight into mathematical modeling in the fields of engineering and healthcare. The conference will provide the researchers an opportunity to present their novel findings. We have several invited talks by distinguished keynote speakers over the span of 3 days, which will enhance our knowledge and ideas about diverse fields. There will be paper presentations both in offline and online mode by various researchers, which will open up new vistas of research and knowledge for all the participants. Last but not the least, about our beautiful temple city Bhubaneswar, I hope your stay in this city is pleasant and enjoyable. Again, welcoming you all. I thank you from the bottom of my heart for being a part of this conference. Thank you.
Thank you so much, ma'am, for your inspiring words of welcome. It is now my privilege to introduce Professor Pradeep Kumar Sahu, Dean of ITER, SOA deemed to be university. Professor Sahu has been serving as the Dean of ITER since 2014 and is a distinguished academician with over 4 decades of experience in teaching, research, and consultancy in payment engineering. An alumnus of UCE Bulla, he holds an MTech and PhD from IIT Kharagpur. He has served as the HOD at CET Bhubaneswar, Dean at CSVTU Bhilai, and PM GSY State Coordinator Odisha. A former NCC officer with the rank of Major, he was also a visiting professor at the Majma University, Saudi Arabia. Sir, may I request you to kindly address the gathering, please?
Thank you very much, Dr. Panda. A very good morning to everybody. On behalf of ITR, I welcome you all to this international conference on computational mathematics for engineering sciences and healthcare. Honorable Vice Chancellor, Professor P.K. Nanda, Honorable Chief Guest, Professor Sanjeeva Pereira, Honorable Controller of Examination, Professor Manjula Das, respected Head of the Department, Professor Sunita Chand, Organizing Head, particularly Chair, Professor Mitali Madhusmita Naik, other leading organizers, convener, co-convener, Professor Kaur, Professor Sahu, all my dear, loving, respected professors present over here, head of the department, my respected teacher, Professor Jishida sir, Professor Panigrai sir, and all my loving students, all participants, mathematics department, particularly busy always in research. I recall recently in the month of February, there was a seminar that is called as Math Talks, yes, in the month of February. And it will always continue. And in 1 year, conducting 2 conferences is a very big thing. But now in the span of only 6 months, 5 months gap, second conference is coming. Internally, maybe more also because very difficult to list all the conferences being conducted by our institute. It's a 30 years old institute. ITR started in the year 1996. Our university, I think 2007. In the last 3 decades journey, whatever the achievements IT has made, university has made, it is very difficult to summarize, but my experience, it is the #1 university in the world. I have gone to United States, I have gone to Japan, I have gone to Canada, and I have gone even in my personal teaching experience in Saudi Arabia, but I have never in such a university. All the scholars, all the professors, all the scientists, all the students are always busy in studying only. That is the peculiarity of SOA University and particularly ITAR. Mathematics department is the nucleus of our college. It's the secretariat of our college, research secretariat, I will tell. All the departments researchers will come, collaborate, and develop very good models. And that will be adopted by lakhs of researchers around the world for future progress. Recently, today's conference, international conference, developing particularly computational mathematics, taking collaboration with health sciences, particularly healthcare. We are, our SOM hospital is here, leading hospital in Eastern India. Though many more things time will take to summarize about our university. Our honorable chairman sir always so generous. What if you are doing research, paper publication, consultancy, immediately it shall be approved. Our honorable chairman also, yeah, vice chancellor also, you see, you are the former dean research. Day and night he had worked several years to bring this university up to such a level. So my dear researchers, particularly for the students, you are fortunate to part of the methods department. The professors, they are always busy in research. Already I have told, mathematics department is just like ocean. All the rivers from various corners will come and merge in ocean. But the banks of the ocean is full of particular waves. But if you go inside the ocean, still completely. You can row your boat comfortably, still water. So that is the peculiarity of department. I am very much thankful to the organizing team members and Professor Naik and Professor Chand also. They came to my chamber also before a few days that we are conducting. It's a good thing. This spirit should continue, and we are always fortunate to part of it. Thank you very much for inviting me to this great occasion. Thank you very much.
Thank you, sir, for your inspiring words. It is now my honor to invite our distinguished chief guest, Professor Sanjeeva Pereira, to address this august gathering. As Professor makes his way to the podium, allow me to briefly introduce him. Professor Sanjeeva Pereira is the Chair Professor of Mathematics and Director of the Center for Mathematical Modeling at the University of Colombo, Sri Lanka. A distinguished mathematician and internationally recognized researcher, he is a pioneer in promoting mathematical modeling for interdisciplinary research in Sri Lanka. His exceptional contributions to research and education have earned him numerous prestigious national awards and international academic affiliations. His current research focuses on applying artificial intelligence, machine learning, and mathematical modeling to understand and manage the spread of infectious diseases. Please join me in warmly welcoming Professor Sanjeev Pereira.
Very good morning, Honorable Vice Chancellor and the Dean and respected academia in the head table, head of the department and academia and research scholars. It's a great privilege and honor to be stand in front of you, provide the evidence to this, I think, a landmark event which is an international conference on computational mathematics for engineering, sciences and healthcare 2026. I believe like that Dean provide the overview of mathematics and providing about like a mathematics department is like a ocean, and also I believe like that the mathematics subject component is the ocean. And I believe that Department of Mathematics timely identify the key component computational mathematics for engineering sciences and healthcare. I think the healthcare is a very important, right? Life-wise, and then every places nowadays we see like that. Now the new diseases are spreading, and also the people, of course, try to I mean, enhance the lifestyle and the other kind of like a health factor. So we need about like that the kind of like a, important point in engineering and the other aspect to enhance the healthcare. When you consider about the engineering, I believe like that the engineering is a workout, right? Workout, and now the engineering, of course, beyond their own traditional domain. We call the traditional domain, this civil engineering, electric engineering, those are traditional, but beyond that now we call whatever the things, working environment, and then the community impact, providing the community to the devices and the various other thing, which is engineering, right? So for example, we call financial engineering, environmental engineering, machine learning engineering. All these workable solution provide the various capacities into the human life. So I think now that here the theme is engineering sciences and healthcare. So believe like that the move workers in the healthcare and providing the engineering aspect and the engineering solution to the healthcare. And why the computational mathematics? I think the as the dean mentioned, also we also believe like that the mathematics is a ocean. Anybody can of course join, and it's a platform where everybody can work, right? Everybody can work. The mathematicians can also cross the different subject area. That's why we have a, like a biomathematics, financial mathematics, environmental mathematics, ecological mathematics, whatever the places we are working in, we call mathematics. And also, why computational? Nowadays, we are in artificial intelligence era. So we try to actually automate the, as much as possible, right? But important point is when you consider about the artificial intelligence, whatever the things we take, but we should consider about the one important factor where human should take the decision, and but we can automate anything, but the human should take the decision. Computational mathematics is a kind of like a way like that the mathematics, statistics, and the all components together in a computational aspect, right? So the Department of Mathematics identify the real need, the computational mathematics era, and using for providing the engineering solution to the healthcare. So I think I congratulate the department and the university identifying the correct domain and the timely important concept, and discuss about the various new domain things. And then so this I have seen like that there are many invited speakers, keynote speakers, so they will actually provide a lot of new domain and the concept, right? So I congratulate the department again, and wish you all the best in this 3-day conference. Thank you.
Thank you very much, sir, for your valuable insights. Up next, I take the privilege of inviting Professor Manjula Das, our esteemed guest of honor, ICCMESH 2026. Professor Das is the controller of examination at SOA deemed to be university. She is a professor of mathematics with an extensive teaching career spanning 34 years. Prior to her current role, she held key leadership positions as the head of the Center for Applied Mathematics and Computing, as well as the head of the Center for Data Science. Her research interests lie in the field of statistics and fluid dynamics.
Thank you, Dr. Abhilip Shah. Very good morning to everyone present over here. Honorable Chief Guest, Professor Sanjeeva Pereira from University of Colombo. Our respected Vice Chancellor, Professor P.K. Nanda. Respected Dean Sir, Professor P.K. Sahu of ITR. HOD Mathematics, Professor Sunita Chand. convener of today's conference, Professor Mitali Madhusmita Naik, co-conveners Dr. Shobhagya, Dr. Pinak, respected Professor Jishidas sir, our ex-professor of this department, Professor Panigrahi, my dear colleagues, professors, senior professors, other faculty members of Department of Mathematics, dear students and participants. Really, I'm extremely happy to come over here because this time this department is conducting consecutively this international conference for third time. Earlier it has conducted, but consecutively for 3 times this year. And in between also frequently department is organizing many workshops. That's a very good sign on behalf of the Department of Mathematics. Regarding the topic of the conference, I would like to say this is a different topic obviously. Computational mathematics for engineering sciences and healthcare. So including healthcare is also very, very important this time. Computational mathematics, we cannot take it as simply a collection of numerical methods or algorithms. It really helps us in bridging the gap between the theoretical ideas and practical solutions, always like applied mathematics. It also enables us to build a safer infrastructure, to design a smarter technology, to give a better solution or a sustainable solution for the society and improve the healthcare facilities. So really we can say that computational mathematics is one of the strongest pillars of innovations in 21st century. In today's life, we can see data is being generated at an unprecedented scale, whether it is satellite imagery or engineering simulations or any other field, even in healthcare facilities. So to extract the meaningful information from this vast data is really a top job. And that is being solved by the strong mathematical foundation provided by computational mathematics. So we cannot ignore it, rather we have to go with it. If we do not aware ourselves with the knowledge of this, then we cannot proceed ahead. So if we move to other fields also, everywhere the role of computational biology is there. In a medical sector also, computational biology, computational mathematics, because it's medical, not biology, it's obviously mathematics. So it plays a very important role. It creates a remarkable opportunities over there. Different type of medical imaging technology we are seeing nowadays, whether it is our CT scan or ultrasound or MRI, everywhere the application of computational biology is there. And with the help of AI and machine learning, it has improved much more. And with this help, even doctors can predict the stages of different type of diseases like cancer, neurological disorders, and even diabetes. It can be diagnosed in advance at the early stages. So predictive healthcare is getting benefited with the help of computational biology. With the advancement of AI, computational biology, with the development of AI, computational biology has got a lot of importance. Because AI is not only about building a mathematical model, it is much more than that. We have to think of that public safety and sensitivity is there. And also the model has to be a very correct one. It should be interpretable. It should be trustworthy. So those factors you have to keep in mind while thinking of computational biology, because AI is also involved over there. And I would like to say, such conferences will help us to exchange the ideas, because an expert in one field cannot grow more. There has to be exchange of ideas, and collaborative research work will help us for today's world. So I'd like to hope that let this conference not only be a gathering of experts, let it be an exchange of ideas, and every idea should convert it to collaborations, and let these collaborations convert it to innovations, and we hope innovations will make or improve the human life. So once again, wishing you all a very successful conference, and congratulate the organizing team for organizing such conference. Thank you so much.
Thank you so much, ma'am, for your kind words and presence. It is now my pleasure to introduce our Honorable Vice Chancellor, Sir, Professor Pradipta Kumar Nanda, our distinguished academician in the field of electrical and computer engineering. Professor Nanda currently serves as the Vice Chancellor at Shiksha Anusandhan deemed to be university. An accomplished researcher, he has authored numerous publications and delivered invited lectures at national. Sir, may I kindly request you to kindly address the gathering.
Good morning, all of you. Jai Jagannath. Esteemed chief guest of this conference, Professor Sanjeeva Pereira from University of Colombo. Esteemed Controller of Examination, Professor Manjula Das. Esteemed Dean of this institute, Professor P.K. Sahu. Head of the department, Professor Sunita Chand. The convener, Professor Mitali Madhusmita Naik, co-conveners Dr. Saubhagya Kumar Sahu, Dr. Pinaki Prasad Kaur, all the distinguished resource keynote speakers from all IITs, all the reputed institute from India, our director of the Center for Quantum Science and Technology, Professor Panigrahi, Professor G.C. Das, who is actually kind of very stalwart, who has contributed to this department. He has worked very substantial time here. All the researchers, faculty members of this department, professors, and delegates from different parts of the country, our own students, students from other disciplines as well, ladies and gentlemen. At the outset, I congratulate the department and particularly the convener and the head for organizing this kind of conference, which is very contemporary and pertinent at this juncture of time. I think, yes, Department of Mathematics is now active in organizing international conference. There is a series conference, I think Dr. Apul is organizing, and under his team. And this is another conference also series. In between, you had a FDP program, machine learning applications, I think inviting all resource persons from across the country and abroad. So this is a very good, I think university has come to a stage that we have been organizing conferences across different disciplines. I think we organized more than 600 conferences last 10 years and across different disciplines. So mathematics department is also quite active in this. And our university has two strong pillars. University has offering degree in 10 disciplines, right from engineering, technology, science, which are in this campus. And we offer also School of Hospitality and Tourism, then Management Science, Biotechnology, then Pharmaceutical Science, Nursing, Medical Science, Dental Science, even Law, Agriculture Science, Veterinary Science also we opened in 2022. So we have I think all professional disciplines are there in our university, and particularly two strong focus are in engineering and health sciences. We have 2 medical colleges, 4 hospitals, I think we have around 850 doctors, researchers, and another 500 all PG students and all super specialized students. So medical sector has a strong focus. So I think at this juncture, mathematics is now has become ubiquitous. Like AI is ubiquitous across disciplines. So mathematics has back end of AI, which is also ubiquitous. And the topic of this is very contemporary application of computational mathematics to the engineering sciences and also healthcare. They are two strong pillars of our university. And mathematics is engineering science is, I think they have been using all the disciplines of engineering and need mathematics, and mathematics also collaborate with engineering science. But of late, healthcare has come into picture. I think we have next generation sequencing machines in our hospital, and we have the very strong oncology department and research group in our hospital who need this kind of thing. I think mathematics they need, but they don't want, they want to analyze data. I think for them, mathematics may not be important. For them, the analysis is more important, but where the mathematics plays a role. So therefore, and also we have pharmaceutical sciences and veterinary science who are dealing with all the virology, all different research, oncology, and I think medicine, pediatrics, all different department. Now we need a lot of kind of the pathology analysis, histopathology. Also, you need a lot of mathematics there in radiology. So now we have been focusing on collaborative effort, interdisciplinary research across the university, because though we are segregated in 5 campuses, we are spread with this with 22,000 students and 2,200 faculty members also. But we try to now collaborate with each other. I actually proactively promote this interdisciplinary approach, and therefore even agriculture has joined with technology for smart farming, and health sciences are joining with also engineering technology. So therefore the veterinary science also using AI. So I think this has become a kind of the contemporary aspect of the research, that interdisciplinary is necessary. No more any segregated expertise will help to address one issue. So therefore mathematics, yes, is quite apt to apply to the engineering science, also health sciences. As for the department university is concerned, this department also contributes a lot towards the research component. I think after becoming university in 2007, we focused on the R&D component, and as of today, we have 21,000 publication in Scopus Index, and last year we had 3,500 publications with all top-notch journals across different disciplines, right from Lancet in medical science to all top-notch in engineering and mathematics everywhere. I'm happy to share that every discipline is now contributing, including veterinary science started contributing, and uh, part of the major share comes from the engineering and science departments, and our pharmaceutical science also is equally good, having international projects like Indo-ASEAN projects and all we are actually running. Also, we are national level labs also we are running DBT builder projects to the tune of 5 crores. We are running state-of-the-art equipments where even foreign faculty members, students come and test their samples in our laboratories. So we have come to a stage where we are now addressing different issues right from different corners of the disciplines. So mathematics will be actually combine all the disciplines, and the base of that, and particularly engineering and AI, this is a key component. I think recently machine learning applications, mathematics application to machine learning was the FDP, and that was there in February. So I believe many such, therefore we have also have a special group in data science, in IoT, in cyber security, and also in AI/ML. So besides the usual routine computer science, we have these many groups, and in data science is full of mathematics faculty we have had, and across from IITs and other places they are doing well. So also other disciplines, AI, ML and all. So there should be now strong collaborations, not only in the institute disciplines, also cross disciplines, like the healthcare, as I told. Even the veterinary science people are more interested to use kind of the machine learning and AI for their domain. I think many of the faculty request me, keep requesting. So I connect them to other faculty also. I am also involved in many parts of the kind of the research activities. So therefore, this is very important, and we have to take out to the last mile of the our students who are there in veterinary science, because for them mathematics is a different domain. Maybe engineering science, yes, people understand, but then other disciplines it will be really difficult. So this is this kind of conference. I wish that you have invited our faculty and students from other disciplines as well, where there is a machine learning component, and we should invite and also invite across the country different disciplines. I wish there will be deliberations, and it is also in hybrid mode, and many speakers are there. I think some of the topics also I could see in the machine learning area. So I wish now application of mathematics is now more important to solve the complex problems. Fundamental mathematics was there, but then nevertheless we need more applications to there, like quantum science. Professor Panigrai and his group uses a lot of mathematics to his quantum science and technology. So similar thing, I think science is kind of perceivable that yes, it can be applied, but the health sciences is a bit different, where we should think and we should popularize mathematics, how to apply them. They need a lot of statistics in medical science, so there is a biostatistics department, and they need in their every research statistical component. So also management science needs statistics. We have SPSS packages for them, and therefore I request the mathematics department to collaborate with our medical science to initiate with, and to go beyond that with, because Bhubaneswar is now education hub where a lot of national institutes of repute are there in medical science and technology and also sciences. So I wish that this will bring together all the researchers, all the new budding researchers who are here and who will think beyond the boundary and think with AI, smart use of AI, how to take it further for solving the real world complex problems. I think that our university will be part of any cohort or the collaborations where you can contribute to address a complex issue of national priority. Thank you. Jai Hind, Jai Jagannath.
Thank you, sir, for your inspiring and visionary address. We now request our Honorable Vice Chancellor, sir, to kindly present a memento to our esteemed Chief Guest, Professor Sanjeeva Pereira, as a token of our gratitude and appreciation. Can we have a huge round of applause, please? May I now request our esteemed dignitaries to kindly unveil the conference abstract book symbolizing the official commencement of ICCMESH 2026. Thank you, everyone. To formally express our sincere appreciation, I now invite Professor Mitali Madhushmita Naik, convener ICC MES 2026, to deliver the vote of thanks. Dr. Mitali Naik, currently working as professor in mathematics, has been associated with ITER since 2009.
Thank you, Abhilipsha. Respected Chief Guest, Honorable VC Sir, distinguished guests on the dais and off the dais, esteemed resource persons of ICCMESH 2026, distinguished members of the press and media, respected faculty members, and dear participants. Good morning to all of you. It's my honor and privilege to deliver the vote of thanks of the Department of Mathematics, Faculty of Engineering and Technology, Shiksha Anusandhan, at the inaugural ceremony of the three-day international conference on computational mathematics for engineering sciences and healthcare. First and foremost, I express my deepest gratitude to our Honorable VC Sir, Professor Pradipta Kumar Nanda, for his gracious presence and his continuous encouragement of academic endeavors such as this. My heartfelt thanks to our Chief Guest, Professor Sanjeeva Pereira, for gracing this occasion and for also serving as a keynote speaker. Sir, your presence and insightful address have truly enriched the academic spirit of ICCMESH 2026. I am sincerely thankful to Professor Manjula Das, Honorable Controller of Examinations, Shiksha Anusandhan, deemed to be University, for her inspiring words of encouragement and motivation. My warm thanks to Professor Pradeep Kumar Sahu, Honorable Dean, Faculty of Engineering and Technology, for his esteemed presence and guidance and unwavering support. A special word of gratitude goes to Professor Sunita Chan, the organizing chair of ICCMESH 2026, for her exemplary leadership, constant guidance, and unwavering support right from the inception of this conference. I would also like to acknowledge the dedicated efforts of our accommodation team, food and beverage team, press and documentation team, the registration team, stage decoration team, technical team, and transportation team, whose meticulous planning and coordination have made this event possible. I express my gratitude to our dedicated PhD scholars, the young mathematicians, for their tireless efforts and enthusiastic support in managing the numerous responsibilities associated with this conference. Their hard work, commitment, and teamwork have contributed immensely to the successful organization of ICCMS 2026. A very special thanks to Dr. Avilip Shapanda, our wonderful Master of Ceremonies, who not only conducted today's inaugural program with grace and confidence, but efficiently coordinated all the inaugural arrangements. I also extend my sincere thanks to the co-conveners, Dr. Sobhagya Kumar Sahu and Dr. Pinaki Prasadkar, for their tireless dedication, and meticulous planning in turning this conference into a reality. Their commitment and hard work have been instrumental in successful organization of this event. Special thanks to our Additional Dean Academics, Professor Dhirendranath Thatoi sir, and Professional Renu Sharma ma'am, the Additional Dean of Student Affairs, for their valuable support and constant encouragement to this journey. I also thank all the faculty members of our department for their wholehearted cooperation, dedication, and active involvement right from the planning stage. A very special note of appreciation goes to our non-teaching staff, housekeeping staff, maintenance staff, whose silent yet invaluable contributions have ensured the smooth functioning of the conference and the excellent upkeep of the venue. I express my heartfelt gratitude to Professor Manas Kumar Malik sir, Honorable Director of ITR, for his constant support and encouragement, which have greatly helped us in organizing this conference successfully. Last but certainly not the least, I offer my deepest gratitude to Professor Manoj Ranjan Naik sir, founder and president of Shiksha Anusandhan, for his visionary leadership, constant encouragement and blessings, which continue to inspire us in all our academic pursuits. If I have been omitted anyone's name, I sincerely seek your forgiveness. Please know that everyone's contribution is deeply valued and appreciated. Each and every one of you has played an important role in making this conference a success. Once again, thank you all for your gracious presence for making ICC Mesh a grand success. Jai Jagannath. Now I would request Dr. Sobhagya Kumar Sahu to kindly present Pinaki. Okay, Pinaki. The other convener, co-convener, Dr. Pinaki Prasadkar, to kindly present the technical schedule of the ICCMESH.
Thank you, madam. It gives me a great pleasure to present the technical schedule of ICCMS 2026. Over the next 3 days, the conference has been thoughtfully designed to provide a rich platform for academic interaction and knowledge exchange. Following the inaugural session, today's program features keynote lectures by eminent academicians, followed by parallel offline paper presentation sessions. The second day will include keynote lectures, invited talks by distinguished experts, online paper presentation, the certificate distribution ceremony, a cultural program by our SOA students, and the conference dinner. On the final day, we'll have keynote and invited talks focusing on emerging areas of computational mathematics, engineering sciences, and healthcare, followed by the valedictory section and launch. We are honored to host eminent speakers from India and abroad, especially Lebanon and Sri Lanka, whose expertise will greatly enrich the conference. We encourage all participants to actively attend the technical sessions, engage in meaningful discussions, and make the most of this wonderful opportunity for learning, collaboration, and networking. We wish you all a fruitful and memorable ICCMESH 2026. Thank you. Jai Hind. Jai Jagannath.
So, ladies and gentlemen, with this we conclude the inaugural session of ICC MESH 2026. May I now request all our dignitaries, speakers, delegates, and participants to kindly assemble for the group photograph, please, which will be followed by the high tea. The technical sessions will commence thereafter as per the conference schedule in this room. Thank you. Have a wonderful day. I request all the participants to kindly come around the dais for the photo, please.
Please say something.
Hello. Okay. Hello. Thank you. How long I have?
Sir, you can start now. I'm already informed.
Yeah. How long I have? Time?
So it's 30 minutes, no? 30 minutes.
35. 35. So which means we are here. 12, 10. 12, 10.
Can the amount wound up in 30 also, we are getting late.
Huh?
Let me introduce.
Right. Okay.
It is on, sir. Okay, sir.
Now on. No?
It is on.
Good morning, welcome again. Let me introduce to the session chair, Professor Arya Kumar Bidabrata. Professor Arya Kumar Bidaprata Chand is a professor in Department of Mathematics at IIT Madras, India. He has obtained his PhD from IIT Kanpur in 2004, following his MSc and MPhil from Utkal University, Bhubaneswar. Before joining IIT Madras in 2008, he served at BITS Pilani, Goa campus, IMA Bhubaneswar, and was a postdoctoral researcher at the University of Zaragoza, Spain. His research focuses on fractal approximation theory, shape-preserving interpolation, radial basis functions, fixed point theory, and computer-aided geometric design. He has made pioneering contribution to the development of spline fractal interpolations,
fractal approximations, and fractal radial basis functions, with application in scientific computing, numerical solutions of differential equation, and machine learning. Professor Chand has supervised 11 PhD students, published over 120 research papers in leading international journals, and has held visiting positions at several renowned universities worldwide. It is my great pleasure to invite Professor Sanjeeva Pereira to deliver his first keynote lecture of the conference. The title of his talk is Forecasting the Invisible Enemy, Computational Mathematics Meets Epidemiology in the Fight Against Dengue. Professor Sanjeeva Pereira is a chair professor of mathematics and director of Center for Mathematical Modeling at University of Colombo, Sri Lanka. He holds a PhD in mathematics DART sandwich program with University of Kaiserslautern, Germany, and an MSc in mathematical modeling from ICCPSISSA, Italy. He is widely recognized as a pioneering in advancing mathematical modeling as a cornerstone of the interdisciplinary research in Sri Lanka. His outstanding contributions to the research and higher education have been recognized through the numerous prestigious accolades, including the National Science Foundation SUSRED Awards, National Research Council Merit Awards, and multiple Vice Chancellor and Senate Awards for the Research in Excellence in 2025. He was honored with the National Educator Award Gold for excellence in teaching, scholarly work, and national contribution in the discipline of mathematics and statistics. He holds international affiliation as honorary visiting professor in Department of Mathematics at the Gandhigram Rural Institute, India, and research fellow at INTI International University, Malaysia. His current work focuses on health impact research, utilizing artificial intelligence and machine learning to model the transmission dynamics of infectious disease such as dengue and COVID-19, incorporating climatic, socio-economic, and behavioral factors. He leads several major research grants on epidemic management and supervises a large doctoral group applying advanced computational and data-driven framework to translate complex epidemiological data into actionable public health insights. May I now request Professor Pereira to kindly take the podium. Let us welcome him with a warm round of applause.
So good morning. Thank you for the introduction. I have chosen the topic forecasting the invisible enemy, and computational mathematics meets epidemiology in the fight against the dengue. So what is so? So basically now I have 35 minutes, so maybe 12, 20 I have to stop, right? So let me introduce, let me explain why I have chosen this, this type of like a topics, right? Since now the International Conference on Computational Mathematics in engineering, sciences and healthcare, so I thought like that now taking the computational mathematics and to provide the solution to the fight against the dengue, which is epidemiology type of things, right? So I am coming from a modeling, mathematical modeling center. First of all, I would like to take maybe 5 minutes to explain about what we do in the modeling center, and then we move into the our basic problem in this ethnology. So this modeling center we established in 2012, which is the main focus, and the main idea is promote the modeling, mathematical modeling research in Sri Lanka, and then especially in the multidisciplinary and the cross-cutting areas, working with the cross-cutting areas. So we believe that now we have, of course, many collaborators in among Sri Lanka. We work with the different subject component, and also now we are now moving into the international collaborators. So let me explain about what we do, maybe few example. One example is what we are working on nowadays, this diabetic retinopathy. This is we have a collaboration with the doctors, right, the medical expertise, and also the physics group. The idea about like that this retinopathy, diabetic retinopathy, now all of us of course aware about the diabetic is a prominent one. So everywhere you can find, and we're talking about like that this chronic disease, right? So the recent years, of course, this retinopathy, of course, the number of the retinopathy patients, of course, increasing, right? Now but specifically the specific expertise who actually try to detect whether the person is suffering with the retinopathy numbers are very less, right? So what this medical group wants, they want to actually use AI type of model, or AI type of like device in order to do the screening, like a first screening, whether the person suffering the retinopathy or not. If it is not, then they can peacefully go home, and then the rest of the people like who detect as retinopathy symptoms move into the doctor's path, right? So what we actually try to use is using the modeling, mathematical model. Of course, we use here the graph theory, and then also the machine learning algorithm, right, in order to develop the basic algorithm for the detection, screening, and also identify the level of the retinopathy. So which we work with the physics group, so they are the basically responsible, of course, making this device, right? Second example, this is kind of like industrial application. I think you are aware about the coconut oil, right? So there are two type of like coconut oil. One is we call virgin coconut oil. This virgin coconut oil coming from pure meat, right? Coconut meat. But there is another type of like a coconut oil which is called RBD, and which of course produced from the dry coconut we call copra, right? So the thing is like that, to detect about these two different coconut oil. One is like that, there is a virgin coconut which is a colorless, right? But then you can look at about that the yellow color which is for the RBD. But now the problem is actually the industry people try to mix up because the virgin coconut oil are very demandable especially in the European market, which is of course because of the cosmetic industry. And the one thing in the cosmetic industry, the other thing is like that the health concern, because I think the virgin coconut oil now all over the world, now the dialogue is between the different group like this virgin coconut oil is good for the health, especially in the heart, and then also that is mitigating the what you call the cholesterol, right? So the problem is like that now due to this high demand and the the people try to mix up the RBD and this one, virgin coconut oil, and also like that even getting the RBD and purify and bring it into the colorless level to identification is really difficult, right? So the industry want to set up kind of like a screening process, and as well as that the produce the device, right? So at the moment, of course, there is a one method using using of course Raman spectroscopy, so we can identify. But the problem with the Raman spectroscopy, which is very costly. Now the normally like that the good one cost about the $500,000 US, and also that you have to keep in a specific environment, like a temperature is very low, and then you have to use in the specific training people, right? So normally in this industry level, it is very hard to use the Raman spectroscopy. So what we try to use is like that, using with the help of this physics group, and then also the industry Coconut Research Institute, we try to actually develop the algorithm, right? So the algorithm which of course cater to the design the specific type of like that the device, right? So we basically use topological indices, right? Indices, because this topological indices which of course represent the chemical graph theory. So based on the chemical graph theory, so we try to identify some of the physical and the chemical properties which are differ from the RBD coconut oil and virgin coconut oil. So that's the second one. So the third one is also another like medical research what we are working on, which is now I think you are aware about the autism, right? So there is a kind of like now the children of course who are of course suffering the autism, there is a huge impact to the hearing issues, right? So what we actually try to identify is like that they develop the kind of like an index where to identify the level of the autism, and then when we treat the children, especially in the autism, right, whether to identify the progress, because the identification of the progress is very difficult, right? So what we thought is like that to based on like that this hearing, right, whether to set up kind of like an index, right? Is also we working with the medical group, right? So the next one we also working with this goldstone, right? I think you are aware about that this goldstone which are very silent, right? Because there is no symptoms, right? It's not actually showing the symptoms, right? When you get like that, if you realize like that you are having this one, but this disease level is in the latter state, right? So then it's very difficult to of course make a kind of like providing the solution. So which also like that we are working on that area, right? Then another point we are at the moment of course we are working on the drought modeling, right? So if it is like a drought, basically we try to find out the damage due to the drought. We call it the pricing the drought, so that now specifically like that the government and the NGO can identify like how much we have to allocate to mitigate the damage due to the drought, right? So those are basically what we are working on. Then of course this dengue research we start in 2009, right? So the 2009, but you know about that why we are really interesting about this dengue. So unlike COVID-19, because the COVID-19 is a shock, right? So it appeared and then disappeared, right? So it's of course somehow we manage, right? But dengue, it's of course according to the history, so 1960 we identified the first patient in Sri Lanka, in the whole of the world, but still like that it's killing the people, and then also the disaster the many socio-economic activities, right? There is no, at the moment also there is no particular vaccine, but of course there were stories about that the vaccine design in Philippines, right? But unfortunately what happened in this vaccine, right, the people who obtain the vaccine, now the next cycle, so they of course the different type of like virus of course attack, and then the most of the people actually beyond, they move into the very severe status, right? So which means like that now the design in the vaccine is also, I don't know, I can't say not possible, but of course like that still from the 1917 to right here still the people are trying, but it's a fail due to the like that now this dengue of course now normally distribute in the 4 type of like viruses, and but each year this viruses of course like a little bit changing, right? So a little bit changing, that's why the main issue, right? So what we actually try to do is now for example now we can find out like that the many statistics, right? Statistics all over the world, right? Especially in the now the world, like globally each year, 100 to 400 million cases reported, and so when it comes to the in the latter status, of course, the severity is of course high. So the lot of people, of course, lost their life, and not only like actually the life, because that's of course the socio-economic aspect, right? I think if you look at about that, this, I mean 2017, Sri Lanka, we failed the hospital management, because most of the patient, of course, we advise actually not to bring into the hospital, because the management of course collapsed. So this year also that we face the same situation again, because after the COVID-19, now this year it of course rapidly of course spreading, right? Now what we actually do there as a modeling, right? Mathematical modeling, what we do, for example, talk about like that this dengue. We know like that now the statistics and other subject component always try to take the data and then utilize about that the pattern recognition and other kind of things, right? But the mathematics, we try to use a concept called compartment type of like a model. So this compartment type of like a model is actually basically, if you consider about the train, so there are many compartments, right? So the compartment, of course, each compartment you can see like that when the train stop at the station, people of course coming in, and then also the going down, and then also like that even the compartment, of course, there are intersections, right? So one compartment to the another compartment, movement of course possible, but sometimes movement is not possible. So we use like that concept, that what we do is like that we divide the entire population into the, generally I can say about that the many compartment. For example, susceptible, which is susceptible is like that the healthy people, so they are exposed to the disease, right? Disease. So for example, if you consider about the influenza, so if influenza infected person close to you, what you do is that you also get there is a possible to get that influenza also. Then those whoever the people got the viruses, they move into the infectious classes, right? Then the infectious classes maybe due to the immunity or even the rest or even the medical treatment, so they of course recovered. So then they are moving into the recovered. So this is a very fundamental concept in, this is called SIR. S stand for the susceptible, I stand for the infectious, R stand for the recovered. I believe like that in these kind of like this SIR model were very famous in COVID-19 time. So we introduced the many other kind of like a quarantine, non-quarantine, and then also the exposed classes, right? So you can expand, right? Basically the idea is like that, what we try to do is now we try to identify the dynamical behavior of the each class, right? And which is basically taking as a differential equation, right? If I show you like that, the very simple idea, I mean there are different type of like diseases, like for example, when you consider the HIV, which is called SI, because when you get the HIV infected, but no recovery is possible, right? So that's kind of like a SI model, right? But when you consider the influenza, which is SIS, right? Why SIS? Because again now you get the immunity from that particular virus, but again you will be of course exposed to the another type of like the thing, right? But we believe like that the dengue, of course, there are 4 viruses. So still we assume like that the recovered is possible actually. So that's why we consider the SIR type of like the model, right? So what we do is like that here concept is very simple. So we look at about that what are the inflow from the susceptible and what are the outflow from the susceptible, right? So very simple example is, if you assume like that now the susceptible person meet the infected person, so that basically like that person of course get the viruses, so they are moving into the infectious. So we believe that then the first differential equation, which is a minus, why that is a movement, I mean the outgoing, movement of the S and the I classes, but there are, of course, you can see like that the beta and various kind of like a parameters, because not everybody, of course, if you get the virus, not everybody, of course, move into the infected classes, because this is depending on the your immunity and other kind of these things. These are very simple ideas, a simple model, right? But what we do is like that, these kind of things. So we know that the susceptible, there are birth, right? So there are birth. So that, of course, you have to include, right? And there are natural death also, right? So we have to consider about all these aspects with this simple phenomena. When you come to the dengue, so human population we divide into the three classes: compartment, susceptible, infected, and the recovery. Also, like there is an agent, right? Because this is not the, the dengue is not the direct transmission like COVID-19, right? Because there is an agent, so the agent is a vector. Vector is basically the mosquito. So they are the actually they are the carriers, right? Carriers. So the mosquito population we divide into the two, susceptible and infected. Probably you might think about the why recovery, because when you look at about the mosquito lifetime is a very short, right? So then the recovery classes is considering about the recovery classes is not, is not, not possible. No need, right? Not possible. So what we do is like that. Now we can see like that the susceptible human. So when me hit by infected mosquito, so then there may be a chance, likelihood that they may move into the infected classes, right? And also like that the susceptible mosquito hit infected human, so there might be like that the chance, the probability or various likelihood that they may, of course, move into the infected class, right? So considering about all the dynamic, you can see that we can obtain the 5-dimensional equation, right? The differential equation, system of differential equation, which is non-linear, right? Obviously, you can see the non-linear, and then of course the parameter space is huge, right? So a lot of parameters, right? But when you consider about the dengue, which is usually like a seasonal impact, so seasonal impact, and then normally what has happened in the certain time it appear and then of course disappear. When you consider about that the short period is like mostly like 2 months, 3 months, and then we can assume like that the human population is constant, so that basically considering about the SH plus IH plus RH equal to the entire population. So we can actually reduce the number of equation into the 3, right? 3 basically considering about that assumption, right? But the problem is like that here there are many parameters, right? For example, you can see the beta H, which is the transmission rate from human to the mosquitoes and the mosquito to the human, and then also you see like that these are heavily dependent on external variable, right? External variable, climate condition, right? Rainfall, temperature, and then the human behavior, whether how much we care about the outside environment, right? So whether we care about we clean the environment, and those kind of things of course matter, right? So the complexity is coming from outside the environment, right? So then the question is like that these models are available, right? Already available, this kind of like a model, but only thing is like that now when we try to use this model, so the realistic nature, of course, we can get if you of course estimate the parameters correctly, right? Estimate the parameters correctly it does not mean like that if you just plug the fixed parameter values, we won't get the realistic nature, right? We are much far away from the realistic nature if you just estimate the parameters in the fixed level, because what we see is like that the outside temperature changing, rainfall is changing, the human behavior is also changing. So because of that, the complexity of the environment complexity, what will happen? So these parameters also the time invariant parameters, right? So if you can actually provide the kind of like a method where how do we actually determine these parameters time invariant, so that we can close to the realistic nature solution, right? That's the one important point, but of course we know about that as the mathematicians, this is a non-linear, and then of course we have to look at about that the stability analysis and all these things, right? So there are that mathematics component is also there. I am not actually touching that mathematical component area, because I just actually try to give you the idea about like that how we work with the now in this artificial era, so to sort of giving the solution, right? Now you see the parameter space, I think I explained about that this thing. So if I actually simulate the previous model, taking like that with the fixed parameters, you will get this kind of like basically this kind of like a solution, right? But actually if I take the data reported cases, so it's like you can see like that the fluctuation, highly fluctuating, right? Which means like that this fixed parameter doesn't work. So we have to actually identify how do we of course estimate the time invariant parameter things, right? So we propose like a various of course like a technique, like we work with this wavelet, Fourier, and various kind of like a fuzzy logic and all kind of like these possibilities. Now of course in this artificial intelligence era, we of course just try to move into which is we call like the physics inform I mean the neural network, right? So the meaning of like the physics inform neural network, what does it mean, right? So just give me give me like maybe few minutes to explain about this one. So generally what has happened in the artificial intelligence, AI type of like these things, so we look at about the data, empirical data, and recognize the pattern, right? Recognize the pattern and provide the solution, right? But wherever it's like that in the data is lacking, right? Mostly in like that now the infectious diseases, one of the key point is like that the data lacking, right? So we are of course having the situation is like that the lack of data, right? And also like that the collecting the data is also difficult, right? And the costly, right? So what is the idea about the physics inform? There we identify the physical phenomena, and then we try to actually develop the neural network model based on this physical phenomena, right? So for example, I can give you the one example. Now if you take the like a water, right? So the water, and then if you just of course mix with this potassium permanganate, you can see like that this of course distributing, right? But if you actually heat up, you can see like that which of course distribute quickly, right? And the entire things turn into the purple color, right? Why? It is kinetic energy, right? The kinetic energy. So we believe like that now these infectious diseases also distribute or spread because of there are kinetic energy, right? What is the kinetic energy? For example, climate condition, temperature, and rainfall, and even the behavior, human behavior. So how much we care. For example, if you clean the houses and clean the outside, so there significantly reduce the mosquito biting side, so that so we can reduce actually the dengue spread, right? So the idea is like that this is actually the potentiability, right? So if you can identify like that there is a potentiability, right? Likelihood, and that is of course the physics, concept of the physics. So we use about this concept of this physics, these potential functions, in order to of course understand and determine the various kind of like parameters, so that it's kind of like that the utilization of the less data and the physical phenomena, so embedded into the parameter estimation, of course physics informed neural network, which is a computational mathematics, and then of course the time invariant simulation, right? That's what the concept, right? I think this explain about these things, right? So what we do is like that this is of course the collaborative project, like we try to actually compare about our modeling aspect into the taking the Colombo area in Sri Lanka and then Jakarta, Indonesia. Why particularly the Jakarta? Because this project, of course, we are working with the one group in Indonesian University of Indonesia, right? So that's why. So we are the both of us, of course, are working on. So the particularly why? Because what we want to, of course, understand is like that this potentiality, right? The potentiality so may depend on the various kind of like a climate condition and the various kind of human behavior things, right? So that's why we have chosen now the Sri Lanka and then also the Colombo and the Jakarta. Of course, now the various climate conditions little bit change, and then also the cultural situations are also different. So that, of course, now all these things, of course, provide the the potentiality for the disease transmission, right? So basically what we do, right? So we just try to, of course, identify some of the data, right? Taking the data, I mean 2008 to 2004, and then we have like that we just try to, of course, identify some of the periodical situation using the well-known like that the wavelet and the fast Fourier transformation, right? So those are the kind of like this, and then those things actually we try to embed it into the PINN, right? And this is kind of like a comparison of the two cities, right? The first red color one is like that the weekly dengue cases, and the next, of course, like that the three different type of like climate condition, temperature, rainfall, and the humidity, right? So this is what we, and then we use about the past Fourier transformation in order to identify that the periodicity, right? So we can see like that now there are differences between the Colombo and the Jakarta, right? Of course, so you can see the Colombo, of course, we have identified that the highest peak like normally in the 26th, that is the frequency, right? 26th week. And then there is another 127, and then wherever the Jakarta also like that the different concern, right? And another aspect is like that we just try to identify the correlations between the dengue cases and certain type of like climate condition, specifically they identify the lag. But normally what has happened like that, if you get the rain today, so we don't get the dengue tomorrow, right? So there is a kind of like a lag, because this now this temperature and then the water of course like that having like a different area. So that of course environment of course motivate the mosquitoes to of course lay down the exam, then the keeping that cycle, right? So we use like the wavelet approach to identify that the lag, and then but these are not the lag of course like that the fixed lag, right? Because earlier of course what we have done is like that we identify the fixed lag, but reasonably of course using this PINN we of course try to of course vary in lag of a situation, because sometimes of course this lag of course vary the different situation, right? Okay, so coming back to the model, so what we try to do is now also we reduce the three-dimensional model considering about that the quasi-equilibrium, right? Yeah, 5 minutes, okay, yeah, 5 minutes. Quasi-equilibrium. So what do you mean by the quasi-equilibrium? Because very hard to identify the mosquito population. What we thought is like that the taking the mosquito population at the maximum level, right? Maximum level. So if we actually find out the solution, the control strategies to the assuming like that the mosquitoes are in the highest level, so we are always in the safety side. So that's what we do is the quasi-equilibrium, and then we reduce to the two-dimensional, and especially we are trying to get the IR model. Why specifically the IR? Is the infected cases, but normally like that now the data of course we are getting the data is infected cases, right? That's why of course we thought of course taking the IR cases, right? Now so there are certain things, we have weekly data, right? The weekly data, because that is the usual thing. Whenever the places, of course, the mechanism, like a health mechanism is like that, getting the data from the different places, but they record it as a weekly, right? But question is like that, the working with this most of like that this AI type of like this neural network. So if you get the week daily data is better. So what we do is like that we just try to of course predict the daily data, of course not damaging to the biological pattern concerning about the weekly of course that the recorded data. So that's sort of our first task, right? And then the second point is like that, of course the temperature and the rainfall, those things usually of course it's easy to of course you can obtain from daily data, right? So nowadays of course there are many satellite freely available satellite data things, especially in like that even the NASA also maintaining the database. So we could of course like easily get the temperature data, temperature, rainfall, all the climate data can be obtained without actually paying anything, right? So that's of course like unlike like that the 10 years ago even the now this temperature, rainfall, those data is also the lacking, and then we just try to of course try to get in the from the med department, but which is very hassle. But now we of course with this freely available what you call the satellite data databases, we don't worry about like that, even though all over the things that we can get the data, right? So we work with the, now this is the basically the our algorithm, right? So the algorithm like that the getting about the data, and then also like that the working with the identifying the optimal lag, right? So the time invariant lag, and then so we feed to the parameter estimation situation, and then also simulate the entire IR model. But of course like that the now the working with the this PINN, of course like the time invariant is working, right? So it's a kind of like a coupling system, right? So this is basically our PINN engine, right? It's not tradition because it's a time invariant, right? We're getting the taking about that the different like a climate conditions data, and then also identifying the potentiability, and based on this potentiability we of course estimate the parameters, right? And these are the comparison between the two cities, like for example now in the Colombo of course weekly validation, it of course provides the R square value with the 88%, right? I think it's basically like that the 88 is very good, but of course Jakarta is I mean the R2 R square value is 97.7, so which is very high, because these are something like that there are some hidden factors also. At the moment of course we considered only the climate condition, right? So we need to actually work with some of the socio-economic impact also. We are now trying to work with those factors, right? So that's why sometimes of course the model work very well with of course like the assuming data, but of course certain cases of course sometimes of course you can see like that the certain socio-economic impact also there. You can see like that now that is a COVID-19 period we excluded, because in that time no human mobility, right? No human mobility, and also like that specifically the people who are at home, they care about their environment, right? So the large scale they clean about the garden and all these things, so they of course they don't have much work. So that's why actually you can see the COVID-19 time the dengue of course reduced rapidly, right? So I think my time is over. He's of course trying to maybe references, and this is what I of course generated from the AI, because to summarize that what we try of course we use the mathematics and then the complexity coming from the environment, and use this computational aspect to sort out the dengue problem, right? So thank you.
Do you have any questions?
Yeah.
So, when you were talking about the data in the dengue example, you mentioned high resolution data.
Sorry?
High resolution data was mentioned.
Yeah.
So, was the data in the form of images or what?
No, actually now these the reported cases now, and also like that now the climate data. So this climate data is a very reliable data because which coming from what you talk about this what you talk this satellite data, right? So satellite data. So those are of course now every second we can get the data, right? No, but if if you go to the basically if you go to the NASA web database, you can get the data as it is. Not, I mean, if you want, you can get the pictures also, right? But if you want to get the data, so data can be of course downloaded, right, directly from them. But those data is you can get the million of data because every second you are getting the temperature, right? So what we do is now we have to of course purify the data. For example, yeah. Yeah? The values are extracted out of yeah. Directly the value, but if you want like pictures, for example, like the cloud density and those things, that's also possible. But what we do. Is it relevant in dengue case? The images are relevant in dengue case, or the time series data is more relevant? Yeah, I think what we actually at the moment we obtain data, right? So not the images, right? Yeah, not images, right? Probably they are not very relevant, I mean, in this example. Yeah, because what we know climate conditions, the rainfall and the humidity, and other thing is like the temperature. Those are the three important data points, right? Data point. But actually about that, the certain cases, most of the cities like in the Colombo, throughout the year, temperature and the humidity is almost same, right? Almost same, like a slightly different. What is actually the potentiability function is coming from rainfall, because rainfall change everything, right? Yeah, but Jakarta is a little bit different because Jakarta is because they are what you call like their humidity also like that we can see the differences, right?
So these parameters are same for both the places, or you have different parameters, whatever?
No, the same parameters, but the value is different because the what we idea is like that the identify the potentiability, right? It's a potentiability of course determined by the external variable because the temperature and those climate conditions. Climate conditions are different, slightly different in the two different cities, right?
But why did you use wavelets? Why did you use wavelets in your method?
Sorry?
Why did you use wavelets?
I didn't get your point.
Wavelets you have used already.
Yeah, wavelet we actually identify that the pattern recognition. Now, for example, like that, what is the correlation between the temperature and the dengue cases? What is the relation between the what you talk about the rainfall and the dengue? Because, for example, now dengue appear today, right? So we try to identify that what is the correlation between the rainfall, right? So what we identified is like that the lag. So there are lag, right? So the 4 to 8 weeks lag.
Directly you can compute using some statistical method. So why do you need wavelets there? Actually?
No, but this of course provide more clear pictures, and then there is a dynamic, right? But the statistics, of course, like that, you get like a static solution.
Okay, you need the variation of time. You need.
Yeah, that's the thing like that, because what we actually identify is like that throughout the different time location. Now the lag is not fixed. Certain time of the lag is 4 weeks, and a certain time 4.5, a certain time 5, something like that, the difference, right? So statistics, what we do is like that, you take data, empirical data, and then you of course identify like the correlations, right? That's all, right? But this one allow us to of course identify the dynamical lag.
Okay, thank you.
Yeah. Correct, yeah.
Okay.
Yeah.
Do you have any questions? Okay.
Yeah.
So if there is no question, let us thank the speaker once again for a nice talk.
Thank you.
Okay, so our next speaker is Professor Milipan from IIT.
Thank you, sir, for your wonderful presentation. It is an honor to now invite Professor Millie Pant to deliver the second keynote address. Professor Millie Pant is a professor and head of department of IIT Roorkee. Uh, she is a distinguished researcher in the field of numerical optimization, evolutionary algorithm, swarm intelligence, global optimization, nature-inspired algorithm, and supply chain management. Professor Pant has successfully led several sponsored research projects funded by prestigious agencies, including the Department of Science and Technology (DST) and the Ministry of Education, Government of India. She has an extensive publication record comprising numerous research articles in reputed international journals, conference proceedings, and book chapters. In addition to her research contribution, Professor Pant has held several key administrative positions at IIT Roorkee. An active international collaborator, Professor Pant has undertaken academic and research visits to leading institutions including AIT Bangkok, Thailand, Norwegian University of Science and Technology, NTNU, Norway, and the University of Leipzig, Germany, fostering global research partnership through initiatives such as DST DAD program. May I now request Professor Milipant to kindly join. Yeah. Welcome, ma'am.
So thank you for inviting me to this conference, and I would now like to start the lecture without any delay. And the topic of the lecture is Significance of Computational Mathematics and Artificial Intelligence in Shaping the Future of Intelligent Healthcare. So we'll first have a glimpse at the background, like what constitutes AI and what you all understand by the term artificial intelligence. So intelligence, if you define anyway, it implies decision making. Okay, we say a particular person or a particular human being is intelligent because he or she is able to make right decisions at the right time. Okay, so that is a very broad definition of artificial intelligence, and it includes a bit of psychology in it and several other topics in it like philosophy, etc., etc. But that is something that we try to incorporate into the machines so that the machines become intelligent enough to make decisions like human beings. Okay, so in the screen you are seeing a diagram, you are seeing a figure about artificial intelligence. So it can be defined in terms of machine learning algorithms or in terms of natural language processing, in terms of expert systems, vision, speech, planning, robotics, etc., etc. Now we look at a narrower picture, and here we are segregating artificial intelligence in terms of AI techniques, which can be in terms of vision, audio processing, natural language processing, knowledge representation, machine learning, and expert systems. So basically, a human being is said to be intelligent if all the senses are working correctly. Okay, if all the senses are working and the person is able to make the right decision. This is a brief journey of neural networks, and we just started very long back, maybe centuries old you can say, and earlier these were the machine learning techniques that were based on some very a strict mathematical background, you can say. Okay, so they were based on some mathematical philosophy, they were based on some mathematical phenomena, and or some statistical phenomena. Then in the era of 1980s to 2000, the neural networks started gaining the different senses, like neural networks got vision, they got unsupervised. There were networks like belief algorithms. Neural networks were able to make decisions. The architecture changed and the neural networks looked like a loop rather than a feed forward direction. The neural networks became loopy, and also the neural networks started to speak. So more and more sensors that were there in human beings were being incorporated in the machines also, so as to make it as intelligent or to make it as similar to that of a human being. Okay, then came an era of deep learning. So this was the era that actually started where we can say that neural networks started moving towards artificial intelligence. Okay, there was a concept of more layers, and also there was no shortage of data. Then there was the significance of brute force was also recognized. We are presently in the decade of deep learning, and LLMs are a type of deep learning only. So now what is happening is the machines are becoming creative also. Besides being able to see, besides being able to hear, besides being able to speak, the machines can now generate something also, can generate the data, and that is known as the generative AI. Okay, that is only one part. Now, the only thing that was lagging till now was the concept of logic in machines. So machines were able to do many things correctly, but still some of the logic questions like you see in the basic SSC exams, etc., or the basic questions like recognizing the shape of something were not being done efficiently by the machines, but that now that problem is also being solved to a large extent. The small picture that you are seeing on the top left corner is the model of a perceptron. That was the very first model that was developed to show the working of the brain. Okay. So how it all started? When did it all start? It actually started out of curiosity. The curiosity to show that the brain can actually be modeled. Before that, brain was considered to be a mystery. How human beings are able to make the decision. Okay, there was curiosity, but other than that, there was mathematics that led to all this. This is the figure which is showing you the bidirectional relationship between the two fields, that is artificial intelligence and maths. These are the two people, these are the two scientists, McCulloch and Pitts, who gave the mathematical model of the working of the brain. McCulloch was a neurophysicist and Walter Pitts was a mathematician. So you can understand that right from the very beginning, mathematics was there, was included. So what they did, they just proposed a very simple model that there is an input and there will be an output. That is how the brain is working. Some information is being processed by the neurons that we have inside our brain, and because of this we are able to make a decision. So that simple concept was modeled, and it was shown that it was able to solve some logic gate problems like AND, OR and NOT. Okay. Then came Rosenblatt, who improvised the model that was proposed by McCulloch and Pitts, and there was one basic difference. He started giving weights to the different inputs that were there. And this is the figure that was shown that actually the problem was that neural networks, the perceptron model, was able to solve AND or NOT, but it was not able to solve the XOR problem. And it was because of the non-linearity. The model was having non-linearity, so it was not able to solve the very simple problem that was solved very easily by hand. So it was said that machines maybe are not that good. So then Rumelhart and Hinton gave the concept of backpropagation, which was existing for a long time in the area of mathematics. All the mathematicians were very well aware of the concept of backpropagation, but it was first time implemented by Rummel, Hart and Hinton in the neural network. Okay, they said that when the information is moved in a forward direction, when there is forward propagation, then some amount of error is accumulated in each step. Therefore, we have to backpropagate, that is, we have to backtrack our steps in order to minimize the error. They, again, what is the concept of backpropagation? If anyone of you knows, it is using simply partial derivatives and the chain rule. Only these two concepts are being used, but it is being incorporated, and till date we are making use of backpropagation. And what Hinton got? Hinton, do you know the name of Hinton? Why was it in news 2 years back? Nobel Prize. Okay, Hinton got Nobel Prize, and the reason was because he gave the basic concepts of mathematics that are being implemented in artificial intelligence. Fine. Okay. Then neural networks started gaining vision. So instead of using the vector notation for the input, now what was happening? The matrix notation was being used for the input. Okay. Matrix, because that is the natural representation for images. Images are naturally in the form of a grid, digital camera. After the invention of digital camera, the images we are seeing are actually the grid structure in which every pixel is representing the intensity. Fine. This is the layered network that you are seeing on the right bottom. That was the LayNet that was proposed by LeCun, and this was the beginning of deep learning era. At that time, this terminology was not there, but this actually started everything, and you can see the grid structure which is representing a matrix. The convolution operator, again, that is a very well-known fact for mathematicians, was being implemented in convolution neural networks. Then another type of data was explored, and that was the data in a sequential format. Sequential format data, what is that? Time series data or the text data. Okay, that is a sequential data, which means that we have to keep the track of the data. I mean, if there is a data in the center, then we have to keep a track of the left hand side and the right hand side. Okay, therefore, this recurrence, the loop is shown there. This is everything in a nutshell, what happened during the time of evolution of neural networks. The current wave is decision intelligence, which means that how we can make the decisions in an intelligent manner. The middle age was representation learning, and initially pattern recognition was there. We can skip this figure. We will come to another figure that is representing you the type of networks that we have. Okay, all these networks are using maths at the core. How the data is being represented, whether it is in a vector format, whether it is in a grid format, whether it is in a sequence format, whether it is Euclidean or it is non-Euclidean. Now we have come to a point that we even consider the non-Euclidean data. Euclidean data तक का यहाँ पर हम लोगों ने देखा है. This is another example. It is an example of vision transformer, which is in the area of computer vision, and how we are breaking down the matrix that we are having. Nowadays, what is happening? We all are using HD cameras. The images that we get are of very high quality. The size of the image is increasing, and from a computer scientist point of view or from an AI scientist point of view, my problem is that the size of the matrix is increasing. So what I have to do, I have to reduce the size of that matrix. For that, what are the different things? The very basic algorithm that you might have done was SVD, decompose your matrix. So decomposing the matrix is still being used, and now currently we are making use of low rank adaptation. You might have heard of LoRa. Okay, so that is where maths is in action. This is the, again, how you are breaking down the image into smaller parts so that the machine is able to understand it. This is another example, and in this figure you are seeing the transition from recurrent neural networks to the transformers. Transformers are the current buzzword in the area of artificial intelligence. Why? Because of the GPT models that we are having. ठीक है ना? Generative pre-trained transformers that we are having nowadays are working only because of this transformer concept. Again, at the back end of it, we are having a very hardcore mathematics, which I've not shown everything here because of the limitation of time. Okay, now we'll come to our our topic of the day, that is AI in healthcare, and we can call it the intelligent healthcare. And this is the concept of intelligence is being integrated into artificial intelligence since a long time, and there are two examples which you might have heard of. IBM Watson. Have you heard of IBM Watson? People from the back? नहीं हो सकता है ना सुना. IBM Watson is there. And have you heard of robotic surgery? Da Vinci robot, उसका ad लगा होता है जगह जगह पे, है ना? So that is making use of artificial intelligence. By the way, there is a case going on, Da Vinci robot, because he performed a surgery wrongly. Therefore, there has been a case filed against it. This is how we are moving on from traditional to intelligent healthcare. So traditionally, it was supposed to be reactive. So once there is a problem, then some action will be taken. And in case, if we are talking about the intelligent healthcare, then it should be predictive. Instead of being hospital-centric, we are now moving to patient-centric. And experience-driven is now data-driven. This is a very important point. And instead of generic treatment, the big hospitals are now moving towards the personalized medicines, and manual diagnosis is being replaced by the AI-assisted diagnosis. So you must have heard the term that data is the new oil, and in the world of healthcare we can say that data is the new stethoscope. Okay, because with the help of data, many of the decisions can be taken. Okay, so in healthcare, your data can be in several formats. Mostly we work on medical images, and I mean my lab works in medical images and also on the structured data. But other than that, there are several other things like electronic health records or wearable sensors, genomics, omics data में बहुत काम हो रहा है आजकल. Then clinical notes are there, and IoT devices. Okay. So computational mathematics is like the engine that is driving artificial intelligence, and all the things that you are seeing on the left hand side, these are the subjects that you read in BSc and MSc. Okay, linear algebra, I'll say, is the most important mathematics topic that is used in artificial intelligence. Everything is based on matrices. Every data can be represented in the form of a matrix. And when there is a matrix, you will be needing all the matrix operations along with the decomposition of the matrices. That is very important. Optimization, of course, is necessary. Why this was not working? I need another port for it. I think this one is not working. So even if you're good with the first 4 topics, that is quite good. The others are more specific and they are used, but compared to the first 4 topics, these are slightly limited. Okay. This is the ecosystem, AI ecosystem in healthcare. First of all, you'll be needing the data. That is nothing but numbers. Machine cannot understand anything but numbers. Everything that you are having should be converted into numbers that are understandable by the machine. Second is the mathematics part, which is obviously the basic mathematics part. Like I said, linear algebra, optimization, statistics, and probability. Even if you know these 4 topics, they are good enough. Algorithm part, now we are moving towards the computer side, how you are managing everything. Those algorithms will form the AI system. Okay, when we say AI, we are actually talking about a broader system. We are talking about a system. We are talking about a machine that is making decisions, that is behaving like human beings. Okay, that if we are talking about healthcare, it will be in the area of clinical decisions and the outcome will be the better patient care. These are some of the computational mathematical tools that are used. So, and again, the optimization methods that are being used in neural networks and in other advanced variants of neural networks are the ones that were proposed long back. Even the Adam optimizer that is used a lot in neural networks was not proposed in, I think that was proposed long back, sometimes in 2018 or 2019. Comparatively new, I mean. Okay. So, but SGD, okay, the gradient descent algorithm, that was centuries old. That was long back. So, that is being used in neural networks in order to minimize the error. The optimization part, one area where optimization is used in artificial intelligence is to minimize the error. There are other areas also, like how you can optimize the number of layers that are there in the neural network, but that will be another thing. The most basic thing that is done in every neural network is to minimize the error, and we have to make use of some optimization technique. Calculus, backpropagation. Probability, we have Bayesian algorithms. Then graph theory, when your data is in the non-Euclidean format, we make use of graph neural networks. We have topology, where when we are analyzing the medical images, and the information theory for feature selection. These are the different ways in which you can classify the importance of computational mathematics in artificial intelligence. And the first block that you are seeing is telling you about the type of problems that we have. In the second block, the applications are mentioned. The third and the fourth blocks are the 2 recent concepts that are being integrated into artificial intelligence. The first one is explainability, and the second one is generative AI. So explainability is very important, and again that is based on some statistical concept that how you can see a particular model is trustworthy or it is interpretable and so on. And with the help of generative AI, we can have medical chatbots, we can use them for clinical documentation, etc., etc. Also for medical education. This is what the big medical colleges looking at nowadays, how we can improve medical education with the help of artificial intelligence. Optimization, so optimization is given more space in this presentation because this is my area, and computational optimization is used in a lot of problems like optimizing the radiation therapy or scheduling the surgery or routing algorithms or allocation algorithms or optimizing the dosage. Then likewise you can make a more advanced model of optimization by considering it multi-objective in nature. This is a small example in which the objective is to deliver the prescribed radiation dose to the tumor while minimizing exposure to healthy organs. So the mathematical part is different, but how you can include AI into it, that instead of manually choosing beam intensity, we can make use of deep learning to predict the beam angle, the beam intensity, and the treatment plan. In the previous lecture, we heard that in our model, the raw data has a number of features. There are millions of features. There can be millions of features. Okay, so we have to extract limited number of features out of it so that our machine can work properly. In that, algorithms, meta heuristics like GA, PSO, D, ACO, etc., work very well. And also, whenever we are having AI algorithms in front of us, there will be a number of hyperparameters that we have to tune, that we have to select. Again, in that case, we can make use of meta heuristics. Okay, these are some recent networks. Like I was telling you that in most of the cases, we considered the data which was Euclidean in nature, but in real life scenarios, you can come under different cases where you are having non-Euclidean domains, when you are dealing with non-Euclidean domains. So in that case, we make use of graph neural networks. An example is shown to you on the right-hand side. It is the example of electronic health records and how graph neural networks are used in it. Another example, physics-informed neural networks. All these networks are the ones in which very strong concepts of mathematics are used, but they are used for specialized purposes. Okay, they are not very generic in nature. The other deep learning algorithms that we have are more generic. These are specialized. When your problem demands the laws of physics, only then go for physics-informed neural networks. Or when the data that you are considering is actually following some sort of non-Euclidean thing, then go for it. So this is an example of physics-informed neural networks for modeling physiological time series for cuffless blood pressure estimation. So like if there is if you are monitoring the flow of blood, or if you are monitoring the growth of a tumor or something, so that will follow some sort of differential equation, and that will be affected by some factors. In those cases, make use of physics-informed neural networks. Okay. Another thing is quantum artificial intelligence, which integrates the concept of quantum computing with machine learning. These are some of the examples. And then in the foundation models and scaling laws, again we have the concept of maths here, particularly for pre-training, fine-tuning, then dealing with the multimodality that we have when we are fusing the data. In case of data fusion, we make use of foundation models are the ones that are used for a specific purpose. Like you can develop a foundation model for healthcare, or you can develop a foundation model for in finance, you can develop a foundation model. So this part we will not go into, but we'll come into the challenges and shortcomings, because this is telling us how mathematicians can, how much time? So how mathematicians can come to rescue. So the first thing is, sometimes we deal with very vast spaces. So how we can reduce the space. Then another is non-convexity. When we increase the number of layers, then the loss function that we get generally becomes non-convex in nature. And we know that in optimization, non-convexity is like a nightmare. It is very difficult to deal with it. There are some algorithmic limitations, and mathematical framework we do not have. That's what prevents it from becoming generic in nature. Interpretability and understanding. So if we have some mathematical theory behind something, then it is easier to explain it, or it is easier to validate it. Not explain, but validate. Okay. This again I'll leave, and again I'll leave this. I'll come to what we do in our lab. So our lab, my core area is optimization. So I work on that, how we can integrate meta-heuristics and other nature-inspired algorithms into AI, and then multi-objective data analytics. If we are working in the area of artificial intelligence, then we need to have an understanding of data analytics, so we cannot escape that. We are working on explainable and trustworthy AI. Then decision intelligence, which is a generic term, but how we can make the decisions intelligently. Okay. These are some of the works, some of the ongoing work, and this particular work is being done under the Lotus Fellowship Scheme. It is a bilateral scheme between India and Japan. One of my research scholars is presently in Tsukuba working on this. It is XAI for, that is explainable artificial intelligence for mental well-being. So just the name change, but at the back end, there is some maths and there is some AI. So healthcare and mental well-being, again, this work is like to understand why some people are more susceptible to phishing, etc. Okay, cyber frauds, etc. We all get calls, we all get some fraud calls, fraudulent calls, etc., etc., but not everyone falls prey to it. But there are some people who are very vulnerable. So that part is trying to be understood. Okay, architectural diagram I'll leave. Then we are also working in the area of neurodegenerative diseases. This work is being done under the PMRF. One of the research scholars was PMRF, and this was the project that he got, for which he is getting the PMRF. And he is working on the Alzheimer's disease, epilepsy. These two diseases he is working on. So there we are focusing on the saliency methods, and we are trying to see which portions of the brain are actually affected during the, like you say, epilepsy attack or something like that. Which area of the brain gets more affected? These are some of the figures, and on the X's you can see the different methods that have been applied. Okay. CAM means class activation map, and the highlighted portions, which portions are getting affected, is being shown there. Then for skin cancer detection, again through images. This detection is being done through images, and the problem that we were having was that deep learning models achieve high accuracy in skin cancer detection, but they suffer from 3 important limitations, like interpretability is low, computational cost is high, and poor performance on minority disease classes. Okay, this is a type of class imbalance. So again, for that we have to make sure that all the classes are equally represented. Image retrieval is another part. You can see the highlighted portion. Here we implemented meta-heuristic evolutionary algorithms in order to optimize. We used it for basic optimization, error optimization, simply for that. We didn't use it for optimizing the entire architecture. That is a much difficult work. And it was a codebook generation. Again here, meta-heuristic was used. This is different, but we have done it in our lab, so I'm showing you that we tried to generate the data synthetically. So it is a big project that is being funded by DRDO. So because of the security reasons, we do not get data easily. So their requirement was to generate the data and to caption the data. IR images are that there. Okay, this portion is not directly related to this particular presentation. This is for, again, it was a smaller project funded by DRDO for object recognition. And this is one area that I was telling you in the beginning, that most of our deep learning algorithms, they are good for solving generic problems, but when it comes to maths or something where logic has to be applied, then it becomes difficult for these models. So we are working on developing some large language models that can easily solve the mathematical problems also. Okay, so we'll end here now. And this is the photograph of Hopfield and Hinton, who got the Nobel Prize. Okay. Thank you, everyone. Any question? Huh? Huh. Yeah. Not the radiologists, because we'll still need to get a second confirmation. Radiologists will always be there. It's not replacing it, but it will help the radiologists in identifying the correct portion, and it will further help the doctors also, that which particular portion should be taken care of at a later stage. No. Okay. So if no question, I'll stop here and we can move on to the next.
Cost exponent for the scaling law, how do you compute that power? Scaling law, do you use any method to get the power?
No particular power, but that is needed.
Yeah, so that
Presently, it is more like rule of thumb, or we just see empirically. But if it is mathematically done, we will be getting better. I mean, that itself will be more, will be validating the entire concept.
yeah. So one can use Horst exponent to get that scaling law. Scaling the power, the Horst exponent, if you can use, you can get it. They are related actually, Horst exponent and the scaling.
Hausdorff law, no? Yes, okay. So thank you, everyone.
So let us thank the speaker once again. So our next speaker
Professor
is
Pant, for your insightful presentation. May I now request Professor A.K.B. Chan and Professor G.C. Das to felicitate Professor Milli Pant. Ma'am, please. Thank you, ma'am. Thank you, sir. We now come to the third keynote lecture of this session. It gives me immense pleasure to invite Professor Prashant Kumar Srivastav to deliver his keynote address. Professor Srivastav obtained his PhD from Indian Institute of Technology, Kanpur, and subsequently worked as a postdoctoral fellow at IIT Kanpur under the prestigious NBHM postdoctoral fellowship. He also served as an assistant professor at BITS Pilani before joining IIT Patna in 2011, where he has been making significant contribution to teaching, research and academic leadership. His research interests span mathematical modeling in ecology and epidemiology.
Yes, that's it. All right, so as we are running late, I guess. So anyway, if you are interested to know, you can search, and then all the information is available on web page. So it's all right. I think we can save some time, and we can utilize that time during lunch. So first of all, thank you, Professor Mithali, for the invitation and the nice hospitality which was provided here. So, is it working or not? There is a laptop which has the pen. Oh. Okay. Yes. वो इस पे काम नहीं करेगा स्क्रीन पे. All right, so what we are going to discuss is some nonlinear dynamics about disease modeling, and then we'll look at that how some mathematical modeling can be applied. I guess this talk will be more of mathematical in nature. So usually this is perceived that mathematics is about abstract mathematical concepts. However, there had been more to mathematical ideas. They are being applicable, and some of the works which I have mentioned here about Ronald Ross. So he worked on malaria model, won the Nobel Prize. RSA algorithm, which you might be aware, that is being used for the cryptography. Then Black-Scholes model, those who are in finance or have done something in finance, they might be aware about this. So there are a lot of mathematical works which has been recognized and which has been given due recognition by giving the Nobel Prize or Turing Award, which are very well known awards. So the idea is that what do we do in mathematics is that we try to understand the ideas, apply them in different domains where we can basically get, or we need to get the information from that domain. So there are empty number of domains which are mentioned here, and the methodology for which we usually apply, we call it as mathematical modeling, which is nothing but in very simple terms, it's mathematics plus modeling. So interestingly, in mathematical modeling, the idea which are involved there, they are about the physical system, because you are going to apply some mathematical tool or some mathematical knowledge. I don't think it will work. यहाँ पे नहीं काम करेगा because it's a screen. ये क्या है? ये ऐसे काम करेगा ना? So if I do it like this, it won't. So when you are trying to apply a mathematical idea on some physical system, you usually refer to the tool, particular mathematical tool which you want to apply. Okay. So usually it depends that how you are trained. According to the training, we apply those mathematical ideas. For example, I had been trained in that core differential equation, therefore I will be looking things from the differential equation perspective. Somebody trained in graph theory may look at the models from the network perspective, and depending on that how you are trained, you will be looking at a physical system and its representation in your core area, and accordingly you want to extract the information out of that system. So that's the very basic idea. I think that's what you will see during this conference as well, that many of us will be showing you the works which we are doing in our domain, and their representation might be completely different. However, at the end of the day, we are extracting information. That is our main aim. We are extracting information from a physical system and trying to give certain information about the system. So how do we usually construct models? So the models which I am talking about are, you can say that they are the theoretical model, or in other words, they are also named as mechanistic models. Is that either these can be completely theory driven models, or they can be like a data driven model, which you have seen the other two talks in the morning, and there can be a mix of both the theory and data driven modeling. So when you look at the diseases, what the diseases are, so basically it's a deviation of an individual from its normal health condition. Diseases are of multiple kinds. Categorically, we categorize them into two major categories, infectious and non-infectious. Infectious means if you come in contact, the contact is a very generic term. However, if you come in contact with an individual and if you are probable to get the disease, you call it as a communicable disease, otherwise a non-communicable disease. In case of communicable diseases, what happens? There is an infection which transmits via the invasion of certain disease causing agents, and those disease causing agents are usually either bacteria, viruses, parasites or fungi, which give rise to different kind of disease. Why it is important? Because when you are doing a disease modeling, you should be aware that how the disease is actually spreading, how it is reaching to the individual, how it is transmitted from one individual to the other individual, so that you can, when you are representing that physical system in terms of mathematical equation, you should be able to write it properly. For example, here a couple of diseases I have mentioned here. The measles, it spreads via respiratory droplets. Chlamydia spreads via body secretions. Most general, the cholera, I think most of you must have heard of, via ingestion of food which is contaminated food, or malaria is spread by mosquito, and therefore the mode of spread of the disease also informs you that how you should try and contain it or how you should control it. Okay. These are some of the microorganisms, and these are corresponding diseases. I have already discussed about it. Why it is important to understand the diseases? One I think most of us have seen this during the COVID time. So one major reason we already have seen, but there are certain other reasons that the total out of the total deaths, the infectious disease contribute to around 1/6, which is roughly 15% of the total deaths. So we can actually contain them, we can control them, and we can reduce those deaths. They also have the impact, socioeconomic impact. They therefore affect the public budget, funding, etc. And therefore a lot of emphasis is being done on the control and containment of the diseases. Had I have some time, I would have told you a story, but nevertheless, the diseases have also impacted our history as well as geography. Okay. So when you write a model, when your models are theory driven, what you do is that you plug in certain assumptions. So in the very beginning, I am going to tell you that there will be certain assumptions. So my models will not be assumption free. That means I am not going to talk about perfect models. They are useful, not the perfect ones. So certain assumptions will always plug in. So when you say the disease spreading, the basic idea is this SIR model. These are very simple equations, and in the beginning of any disease, if you see, most often the modelers, they will look at this very basic idea. This is like foundational idea, and they will build upon this foundational idea and try to write equations. Okay. So what the SIR model tells is that healthy, S means susceptible are the healthy individuals who have no infection, and I means infected individuals are infectious individuals, depends on the context in which you will be using, and R means recovered individuals. So healthy individuals, this negative rate means that they are becoming sick. Those who are becoming sick, they will be added to the infected individuals, and then there are certain individuals who were sick earlier and not sick anymore, becoming recovered that way, and therefore this whole professor was mentioning the compartmental model. So this is what the compartmental model is. You are like in the total individuals, you divide them into three parts. Call one part as healthy individual, the second one as infected individual, and third one as recovered individual. And imagine that as time passes, people just leave one compartment and move to the other compartment. So somebody was healthy, got infected, sits in the next compartment, again further time passes and got recovered, then moves in the last compartment. So that's how the compartmental model. So it's a flow of actually the individuals. Now, this is one important information when you write about the write about the disease models, you calculate the basic reproduction number. What does the basic reproduction number tell is that how many new infections are being generated, how many new infections are being generated via one single infected individual in completely susceptible population. So if the number which are being generated by one infected individual is larger than 1, then you see that the disease is going to sustain in the population, otherwise it's going to die out. So it's a very important number. Most of the analysis will be around this number. Okay. So this particular part of the talk I have based on this particular work. If you are interested, you can look at this one. So in between I will keep on sharing these QRs. So if you are interested, you can find this. This is open access, so you can find it, you can actually access it. So this was actually, this work was done. I'll be skipping quickly. So if there is a question, later on we will take the questions. So this work was done when the COVID was spreading, and it was the period of that is March 2020 to somewhere around July 2020. So that was the period when we have considered this modeling. So what was at that time, there was no available information, not better information was available. Whatever was available is that you try to change your behavior, try to put masks, etc., and then therefore control the disease. Okay. So what we did here is that we divided that population, as I mentioned earlier, 3 compartments. Here you can see that the multiple compartments are there, which 7 in number. So healthy individuals, they get infection from these IS and IA. What is the IS? IS is the individuals who were symptomatic. Symptomatic means those individuals who are showing the symptoms. And then if you recall, if you recollect, during the COVID-19, there were individuals who were not showing any symptoms, right? Or rather who were not, they might have contracted the disease, but you never know that they are basically infected individuals, and therefore they were also spreading the disease. So we had considered during that time that certain individuals who are infected, whom we know that they are infected, but certain individuals we don't know that they are infected. The data which was coming at that time, if you see the COVID-19, that was only for those individuals whose RT-PCR test was positive. There was a certain test which ensures at that time that these individuals are actually infected. That means we have the information of these individuals only, but in the population there might be some other individuals as well. So healthy individuals, they are exposed via infection of these infected individuals. There are 2 flows, if you see here, which are contributed by symptomatic as well as asymptomatic. Now from the exposed individuals, certain individuals will get into the symptomatic class, certain will get into asymptomatic class. Symptomatic, since you know that they are infected, they need attention, medical attention. So you either keep them in the hospital or you keep them separated from the population. So these are the individuals which will, so H is standing for that one, that they are the patients which are in care. So H stands, although the word is for hospitalization, but it stands, which we have written in the paper, it stands for those who are in the care. Now asymptomatic individual, the policy was there at that time, if you have the contact tracing, and you know that these individuals have come in contact with infected individual, you should keep them in isolation. Okay. So these individuals, if we are aware that these individuals have come in contact via some contact tracing, they were kept into isolation. So this QH is referred as the quarantine class or the isolation class, and anybody who is recovering was going to the recovered class. And then there are certain other flows which are representing that there are disease related death rates, for example μS here, μH here, and then asymptomatic individuals were also becoming symptomatic individual via test, either RT-PCR test or via showing symptoms. So somehow if any individual is showing symptom or if any individual's RT-PCR test is positive, we are counting that person in IS class. Once you have model, mathematically we analyze it and then we try to extract information out of it. Due to the lack of time, I won't be probably looking at all those aspects. What I will do is that I will emphasize couple of points here. What was novelty here was in this particular model is these 2 parameters which are epsilon m and Cm. Epsilon m refers to the efficacy of the masks which people were using at that time, that how effective your mask is. If it is 100% effective, naturally it is going to do good, and then the infection will reduce. And CM stands for the compliance. Although masks were good, people were not using masks the way they should use. Some people were using on chin, some people were not using, maybe covering mouth only, or some other ways they were doing it. That means if you are not, even if you are using the best masks, the compliance is not the best, you will have the problem, which we have shown later on. So these are certain interventions which we have introduced within the modeling framework. So this is your efficacy, this is compliance of the mask, and then so on and so forth, and then other one was asymptomatic, converting into the symptomatic, and then so on and so forth. So on the basis of this flow diagram, we have this model equations, and these are the explanations of these parameters. So when we took the data, now there is huge problem, okay. So if you look at the model equations, there are so many equations, there are so many parameters, but the data which you get, that is always limited. So if you want to do any kind of scientific study in any area, you will realize that later on you have all kind of problems, okay. I am talking about this particular one. So the data which we use usually for parameter estimation, that comes from somebody who is from the health sector. They will be providing us data. For example, in this particular case, the data which is available, that is only of IS, or the infected individuals whose RT-PCR test is done. So why is it so? I mean, when I am writing those equations, I have these many equations, right? Now somebody is providing me just one information, which is here. So how should I do? How should I estimate my other parameters? What should I do? Okay. So we have to figure out a way. We have to figure out a way, because nobody is going to work for us. Rather, those who are collecting the data, they don't know that one day somebody will come, make a model, and then give me some information. What they are doing is that they are doing their job. So we have to extract information from what they have already done. So that happens in any area, any kind of problem. You will always find that data will always have one problem or the other, because the person who is collecting the data is not collecting the data for some modeler. They are collecting the data for their own purposes. So we also had a problem here, and then what we did is that in order to estimate these parameters, we focused which parameters are best representing our information. So we took the beta one, and I think we took alpha H. Alpha is the recovery rate of the quarantine individual. That means because quarantine individuals are those individuals who are asymptomatic. That means their presence was having a major impact on our overall. So this is some mathematical analysis, I will not get into that one. Our overall dynamics. So certain parameters we assume, certain we have taken from the literature, because that is the best way you can do. For example, some demographic parameter you can take from the population, and this is the data which was available at that time. These are the 3 states, Maharashtra, Delhi and Tamil Nadu, and this one is for the whole India. So this is the data for 100 odd days, that means 3 months starting from 20th March 2020. And we estimated the parameters, 2 parameters only we estimated, because if we estimate multiple parameters, our prediction might not be that correct. So when we estimated the parameters for these states, we could found that the basic reproduction number which I was talking about, that comes in the vicinity of these numbers. And then on the basis of that, we have fitted our model. Basis of that, we have found that these are the patterns which we can get. Again, so this information which we got, that comes with a caveat, that this is not the perfect information which we are getting. These predictions cannot be perfect. However, these predictions will definitely that what is going to happen in the near future, if not in the longer future. So near future, you can see that the pattern that it was showing that the cases will be for A is for Maharashtra, so the cases will be on the upside. For the Delhi, the cases will be subsiding, and then for Tamil Nadu also cases will be subsidizing. However, for the whole country, because there were a lot of states which are involved, the cases will be on the upside. And later on we saw that these predictions were on the same pattern as we have found, but maybe the numbers might have been different. So we have also gone for that what should be the compliance, what should be the efficacy. So this is how mathematical modelers do. They try to figure out that what if. So big what ifs are there, those questions we raise and then we try to answer those questions. For example, here we have tried to answer that what if the efficacy and the compliance, so these the values 0 to 1, that means from 0% to 100% efficacy, 0% to 100% compliance. If that is the case, then what will happen in the state of, first one is Maharashtra, okay, and then this is the pattern which you are following everywhere. This is the basic reproduction number when R0 is equals to 1. So this is what we have plotted for R0 is equals to 1. So below that, if you see the colored bar here, the below one is the red color. So that means if the compliance, if the efficacy is higher, compliance is higher, you will be landing somewhere here. Both the compliance and efficacy higher, you can actually find out that for what kind of efficacy, what kind of minimum compliance you need. For example, if your mask is of 80% effective, then you will find that minimum of 55% compliance you need if you want to have the elimination or even the control of the disease. So this way we have extracted the information. We have gone for the other parameters as well, but I don't think that we'll be looking at it. I'll invite you to have the look at. So during that analysis, we have found the different cases that what should be the various combination of the parameters and how the disease will actually. So this is the symptomatic population means IS, how the symptomatic population will change over a period of time. So you can see that most often it has a decreasing route, okay. I'll show you one more example and then probably I'll be stopping here and then that will be done. So usually when you control, you also have the problem that what kind of control intervention. So this is another work of us which is from the infectious disease modeling. You can also access it if you want to. So here we have shown that how much, so when you apply any control, any kind of control measure you are going to apply, there is always a cost involved with that one. That cost can be of any kind. Cost can be monetary cost can be human resource, cost can be anything. So that cost is always involved. So for this particular case, we have considered, I'll show you. So the idea, this was the novel idea which we used, IDIAS, which we referred as additional screening due to infectious disease, due to infectious density. So infectious density induced additional screening. That is what the full form is, IDIAS. So when the infection, when any infection increases, the public health worker, they try to put their effort. So in case of COVID-19 also it was happening that when there is infection is going to increase, they will put additional screening in place. That means they will increase the resources, the available resources. So this is our bottom, the baseline screening, and this is the additional screening, which is a function of infectious numbers. This is taken as a saturation because after certain time your capability of screening will be leading to some saturation. In addition, we have also found that the treatment was also not available to everyone who wishes for, and therefore that should also be a function of this kind. Both these functions tell that as long as I becomes larger, this number becomes constant. You can put the simple limit condition here. So this is the model which we consider susceptible becoming, so exposed class we have removed from here, becoming IAIS as in our previous case, then they are moving to the infective in care, and then they are moving to the recovered class. And then we have also understood at that time, because by the time this study was done, the COVID-19 was believed to have reinfection because other variants were also coming. So we have also considered the cases of reinfection. So this is the model equation, reduced 5-dimension model equation. And now again, what we did, we again were influenced by the information which was available, as I mentioned earlier, because the data was collected by somebody else. So what we did is that we have considered the cumulative infectious cases. Cumulative means total infectious cases, and we wrote an equation for that one depending on my model. We wrote an equation. So instead of fitting the IS which we did earlier, now we fitted the cumulative data because that is what which was available to us. So that's how we have changed our strategy. And again, mathematical analysis, because we are want to see the robustness and all those things. So this is the data which was there. Now the data Since we are working on additional screening, in India we could not find the data which is supported by additional screening, or where the, we could have that, okay, from this date onwards some additional screening is started. However, luckily we got the data from the Hong Kong, where it was very well established and it was very well mentioned that additional screening is being employed when the infective individuals are increasing within the population. So we fitted the data and we made certain predictions here. So we made certain predictions. So this is our fitting timeline. This bar 59 days which the data is available, and then this is the prediction timeline. Depending on that, the saturation and the baseline screening and the additional screening, they were based on that one, and it could be easily seen that if you don't have additional screening, the infected individual will increase all of a sudden, and if you have that additional screening, then the individual that infected individual will remain there. So we could find that additional screening that plays a significant role when you are putting them into the system when the infective individuals are increasing in numbers. We went for understanding that how good this additional screening strategy will be. For that we use the typical optimal control analysis optimization, dynamic optimization, and we observed, I'll show you just one or two results. So we use certain strategies. So this one strategy C, I would like to I would like to your attention towards this one. This is boosting additional. That means this is what the idea is, the novel idea which we have incorporated in this model. And then we found that how these strategies are impacting the cost here. But if you look at many of them are not have huge difference, and therefore we found them. So these are the cost associated and cost incurred in this table, but we wanted to know, okay, which strategy among them. So suppose if you have 2 or 3 strategies or 2 or 3 ways through which you can control, and you want to know that which one is best among the best, okay, there might be better, because again each strategy, for example, if you want to provide treatment, that treatment will have its own limitation. If you want to provide vaccination, vaccination will have its own limitation. 1 minute only. Vaccination will have its own limitation. So therefore, even if you have multiple options to control, among them also you can utilize that which one should be used and which one will be the best one. So this costs here were telling us the story that this is how you should apply them. However, when we went for this ICER incremental cost effective ratios, we found that this C is becoming the best one, because ranked 1 and then second and third. So among the strategies which we are using, they were ranked as first. So the additional screening came out as the best one for the data and all, for the data which we have used. Okay. So this you can see that this has the minimum cost effective ratio, and therefore we consider it as the best. So I think I will be stopping here, and yeah, that's it. So we'll be happy to take 1 or 2 questions if you are still not in hurry for your lunch.
Questions from the audience?
Any question? If there are no questions, then maybe I'll go for another model. Yeah.
Students are happy with your presentation. They understood everything.
God knows. So there is one announcement. If you are interested, you can. So this is the society where I am in a leadership role. So if you are interested, you can scan this one, and there will be a conference.
Thank you, sir, for your excellent lecture. I now request Professor A.K.B. Chand and Professor Milu Acharya to felicitate Professor P.K. Srivastav. Thank you, ma'am. Thank you, sir. We now break for lunch. Thank you and enjoy your lunch.
We will have lunch in E522, and after the lunch, you can go to your respective rooms and for the technical sessions, parallel sessions. The today's second half only will be for the present paper presentations, that is the parallel sessions. Again, tomorrow morning we will be having the lectures in 414. We will be notifying that in the participant groups. So please make sure you are at the paper presentation venue by 2:45 to submit your PPTs to the session coordinators.
I thought in NIT he's from that. Oh, you were from IT? MS? Which year? 15 to 17. I see. Okay, 15 to 17. So now you are the faculty here? Oh, not his PhD. Okay, I thought that you must have gone for PhD somewhere. Yes, first thing first, find out the interest, that what is your area of interest, right? And then accordingly choose. Now, if there are some places where, I think here also they might be doing this one. So in some places they will allow you while you are in your job. They will allow that PhD, that, yes. So for some time you have to do coursework. I can keep it here, right? For some time you can do some coursework. Even like in IIT Patna, they even give more freedom. If everything goes fine,